Hi, I'm Chris Brown, and this is the third module on intermediate axiomatic design. I'm a professor in the Mechanical Engineering Department at Worcester Polytechnic Institute. This module is on decomposition techniques in axiomatic design. So decomposition. So when a practitioner develops a parent FR to be decomposed, the composition of that FR might be unknown, in other words, the details. And so essentially we're starting off with a working hypothesis that there is a decomposition that will lead to a detailed design solution and that the designers are capable of developing that detailed solution. The process of decomposition attempts to provide details of the design in the functional and physical spaces and thereby test the hypotheses. We could also include process space there as well. So we could look at the decomposition, the lateral decomposition that we've spoken about as kind of narrowing the scope from why to what to how. So there might be many things that could fulfill the CNs, and then we select certain FRs, then we select certain physical solutions, and then certain process solutions. So here we've emphasized the FR and the DP space. So as we decompose these, the point that I was trying to make in the previous slides is that the solution is essentially all there in the upper level FR, and we just have to figure out how to break it out, just as it is in the DP. And so so what we're doing then is dividing this up into subsets, essentially. So here we have the FRs and the DPs down to the next level, and then we could have to the next level. And then at some point we reach what we call the leaf level, or the nuts and bolts, and at that point the solution is obvious. We have enough details, we don't need to decompose further. So what we've done then is we've gone from the abstract up at the higher levels through increasing detail to the detailed solution. So there's the essence of the decomposition, and we spoke in the previous section about how to develop some of the FRs. So here's another way of looking at this, is kind of set theory. So we have the set S at the higher level, and then we decompose it into some M number of subsets. And if we add all of these together, they equal the parent. So the sum of the children equals the parent. And so in this way, what the decomposition essentially does is it articulates the details at successive levels. So the elements, we could imagine, at the lowest level are already in the high level. We just haven't figured out, perhaps, how to articulate them yet. So, as we've said several times now, good FRs must be semi-min. Collectively exhaustive. Did we think of everything? Because if we haven't been collectively exhaustive, then some part of the solution will be missing. Only a collectively exhaustive decomposition can be complete. Mutually exclusive. We want to avoid redundancy, overlap, keep it simple. Children that lack mutual exclusivity will be coupled and thereby inhibit compliance with the independence axiom. So mutually exclusive decompositions are required in order to maintain independence of the functional elements. Axiom 1. Minimum number, only what is necessary, simplify. So if it is collectively exhaustive, it is mutually exclusive, there is only one number that should be right. But applying minimum number often helps us to find things, as in the example in one of the previous modules on forces and moments. So anything with more than the minimum number of children would be redundant and suboptimal. So at each level, the decomposition hierarchy sum of the children equals the parent. So sum of the children equals the parent. And this helps to ensure CDMA. So decomposing by products. So FRs are verb-noun pairs. So many times we can just decompose the noun at one level and the verb at another. It's like taking the derivative of products. We might think too the way taxonomies decompose from general to specific. So they're looking essentially for the commonalities in the creatures at the higher levels and differentiating them. So lowest levels of the greatest physical similarities. So here's development and verification of digital systems decomposition. And so you've got at the highest level objects and classes, code, RTOs, and so you can see how data control and or control and data merge work in software domains. So there's a similar kind of problem. And again, the sum at the lower levels has, in this case, has got to be less than at the upper level, and has merging, scheduling, and separate things. So those are added functions. So taxonomy of tasks in virtual environments. So here's another example of a decomposition, graphical example. So the selection technique is decomposed into feedback, indication of object, and indication to select. And each of those is further decomposed. So the idea here is that there are other fields that also practice decompositions, and they have the they have this in common. They have something similar with the decompositions that we're doing. The point is that we haven't invented something new by doing these decompositions. We're following a long tradition of taxonomy and combinatorics and classification. Now, prioritization. Sometimes you have competing subsystems that appear to be influencing each other. You might have, say, a fuel cell that is supposed to be environmentally friendly. And so you have an FR for sort of the protecting the environment and an FR for creating energy. Which one comes first? How do you keep these things from being coupled? And so that's what we're going to take a look at here. Now, in the third section on this, we'll take a look at the derivatives and this differential form of the matrix. So what this is telling us, though, is the change in R, FR due to a change in the DP. And so we can take a look at the matrix elements in the design matrix as being partial of an FR with respect to a partial derivative of the DP. And so that's what we're looking at these different points. And so we're looking at a kind of problem where we can say that DP1 is influencing FR1 and FR2. DP2, of course, is influencing FR2, but there's a question here about how important it should be. For example, should the environmental aspects be influencing the power or not? So here's one. Now, releasable ski bindings have been around since the late 1940s in some form or other, intentionally releasable. But the job of the ski binding is to provide self-control load transmission. And the DP0 there should be safe control load transmission systems. And so FR1 is to transmit the control loads, and FR2 is to filter out potentially injurious loads. So if the ski catches on something, for example, it won't transmit enough torque to the leg to break it. So in the first time of the DPs, we're just talking about systems. And again, we have this, so DP1 the control load transmission system is going often interacts with the filter injurious load system. And so the question is, does the DP2, the injurious load filtration system, interact with the transmission of control loads? If it does, we should have a concern there, because release will prevent transmission of control loads. So one question might be, would a ski binding ever release unintentionally when the leg is at no risk of injury, and then the subsequent loss of control might put the skier at risk of injury? So here's a sequence of a young ski racer in central New York, and does not appear to be at any risk here, making a turn, and then suddenly the ski releases from his foot. So now, with only one ski on, there is some risk, significant risk of losing control, which is starting to happen here, and then a subsequent fall, and the associated risk of injury. So in this case, the release function increased the risk of release, risk of injury, as opposed to decreasing it. So what's going on? So the injurious load transmission filtration system can interfere with the transmission of the control loads. So the designer needs to commit to fidelity in transmitting control loads and put some sort of constraint on the filtering system. So how can this be done? This is what we would like, is to have at least a triangular matrix. So we can introduce another FR, and then we need to have some way of limiting the inadvertent release, and that might be to absorb energy, essentially, at sub-injurious loads. So sub-injurious load energy absorption. If we had that, then that would not interfere with transmitting control loads and would not interfere with filtering injurious loads. So that would be a good system if we could figure out how to do it. So if we looked at sort of, here are the loads that might be transmitted, and here is the displacement. And so this might be the current situation. You load up to some point, getting up until you're up above the normal control loads, but below the injury load. You absorb a little bit of energy, and then you have a release. So if we could adjust this and absorb even more energy before release, staying below the injury threshold, then we would have a binding that would be less susceptible to the kind of inadvertent release that we just saw. So that's a kind of prioritization. So one more example of prioritization. So let's think of a fishing boat, maybe like a lobster boat. So FR1 for the boat might be to provide seaworthiness, and FR2 might be to catch lobsters. So one of the things we note is that when we're hauling up lobster traps, there's a lot of tension on this rope, and there's a little power puller. And we can see how the boat is now listing strongly to starboard. So there seems to be some risk here for DP2, which is going to be the lobster catching system. We certainly want that to help us catch lobsters, but what's it going to do to the seaworthiness? Because after all, there are things more important than catching the lobster. Catching the lobster is not the most important thing. Let's be sure that the lobsters don't end up with the boat. So in these situations where we seem to have sometimes a priority question, we have to decide what's the most important. If the fuel cell doesn't produce electricity, nobody really cares what else it does. If the lobster boat doesn't return to port, we really don't care how good it was at catching lobsters. So the designer needs to make sure in these cases that the DP for catching lobsters does not interfere with the DP for seaworthiness, or somehow, for example, in the case of the ski binding, that the DP for filtering out the injurious loads does not adversely impact the transmission of the control loads. So some concluding remarks. So lists and themes can help with decomposition, but they cannot replace intelligence. And we need to have some kind of prioritization to escape this coupling that would lead to a fully coupled matrix and then would not be adjustable. Thank you for your attention.